All right, so we're going to do some examples from section 11.5, which is lines in space. We're going to do exercise 4 on page 741 of your textbook. So in exercises 1 through 7, find a vector equation, parametric equations, and symmetric equations for the line that contains the given point and is parallel to the vector L. So they give us the point, which we'll call P naught, negative 3, 6, 2. And our vector capital L is 1, negative 1, 0. So they don't have they have it in the textbook written as this is I minus J, but the way that we tell that we're actually in 3 dimensions versus in 2 dimensions, even though they don't have a K on here, is the fact that we have an X, Y, and Z coordinate on our point here. So if this had only had an X and Y coordinate, then we would know that this was just a vector that's in 2 dimensions. But because of that Z coordinate there, I knew that I needed a K component of 0 on my vector L. So first, we'll start with the vector equation of a line. So just as a reminder, I'll get what the equation is. So R equals R naught plus TL. So here we see what our R naught, we just take the components for R naught just come directly from that point P naught. So this is R equals, but now we're going to use vector brackets, negative 3, 6, 2 plus T times, then we just put in our vector L and we're done. So 1, negative 1, 0. And that's the vector equation. Now, from the information that they give us in order to set up our parametric equations, let's go ahead and pull out what is our X naught, our Y naught, our Z naught, our A, B, and C. And of course, we could have done that from the very beginning. But in order to prepare us for parametric equations, we'll do that. So parametric equations. So our X naught is negative 3. Our Y naught is 6. Our Z naught is 2. Our A is 1. Our B is negative 1. And our C is 0. Now, the formula for parametric equations, though, is X equals X naught plus AT, Y equals Y naught plus BT, and Z equals Z naught plus CT. So we just plug in the information that we have now. So X equals negative 3 plus T, because our A was 1. Y equals 6 plus, 6 plus negative 1 T. And then Z, our C is 0, so Z just equals, what is our Z naught? Z just equals 2. All right, so those are our parametric equations. Now, lastly, we'll do symmetric equations. And just as a refresher, those equations are X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. All right, so we're going to plug everything into here. So we have X, our X naught was negative 3, so X minus negative 3 over our A, which was 1, equals y minus our y naught, 6 over our b, which was -1. And I would go ahead and naturally say equals and put z minus, but we have to be cognizant of the fact that c is 0. So the fact that c is 0, of course, we know we can't divide by 0. So if you think about the way that we come up with the symmetric equations, what you do is you solve each one of the parametric equations for t. But we can't solve this z equals 2 for t because there's no t in there. So our symmetric equation aspect for z is going to be exact same as it was for parametric equations. It's just still z equals 2. So that stands alone though. Z equals 2. So you don't put an equal sign right here. So these are our symmetric equations. Now, we put these together, but oftentimes you'll be given symmetric equations and you'll have to squeeze the information out of them. What is your point P naught? What is your vector L? So you should be able to look at this and tell quickly what your P naught is. Your P naught is going to be -3, then 6. Remember, this always has a minus sign, then 6, and then 2. All right, so you can see that clearly that way. But you oftentimes won't be given symmetric equations this way. They'll be simplified. So if I simplify this will say x plus 3 equals, and here if I brought this -1 up, that would be -y plus 6, and then z equals 2. These equations are the exact same as those equations up there. So be comfortable going from this simplified form into the unsimplified form so that you can make sure you can pull all the information out of here. It's not very easy to tell what L is in this form. You would know that your K component of L is going to be 0 because this is standing alone. But this, you might think, oh, well, I can put this over 1, and that tells me that my J component of L is 1, but that would be incorrect, though. Your J component of L is actually -1 because this has to be in the form y minus y naught. So that's what you would do is you would take the factor out of negative, bring it down to the denominator, and you will get this, and then you can see that your J component actually is -1. Similar thing here. You could put this over 1 and you'll be fine. But for finding your x naught, you have to be careful. Your x naught is not 3. This has to always be of the form of x minus. So you would have to change this to x minus -3 so that you can see your x naught is actually -3. So be comfortable if you're given symmetric equations in their simplified form, going to the unsimplified form. All right, so the next thing we're going to talk about is how to find the distance between a line, script L, and a point that's not on that line. So the distance between a line, script L, and a point, which we'll call P1, not on script L, is capital D equals the length of L cross with the vector P0 to P1, the length of that cross product divided by the length of the vector L. So let's define what our capital L is. We know what that is because we talked about that. And then we'll talk about what our P0 is, which is going to be the same as it was before as well. But where the vector L is any vector parallel to script L, and P0 is any point on script L. All right, so one thing to be cognizant of is that remember, for all of these things that we've discussed, we have some line script L. So whether we're talking about vector equation, parametric equation, symmetric equations, the distance, it doesn't matter. The vector capital L is any vector parallel to the line of your choosing. So you, in all likelihood, are going to choose a different vector capital L than somebody else would. And same thing for your P naught, is any point on your line. So don't expect your equations to look exactly the same as somebody else's equations. They actually are equivalent, but they might not on the face look exactly the same. So please be careful of the fact that, or be cognizant of the fact that this is any vector that's parallel to L, and that's any point that's on your line L. All right, so let's look at an example of how to find the distance between a line script L and some point P1 that is not on the line. So we're going to look at number 20 on page 741 of your textbook. So number 20 says, find the distance d from the point 2, 1, 0 to the line with equations x equals -2 and y plus 1 equals z. All right, so they told us a point where the point 2, 1, 0 is not on the line. So we're going to call that P1 because that's how we define that. So P1 is 2, 1, 0. And then they gave us equations of a line. So the equations of the line are x equals -2 and then y plus 1 equals z. So we can quickly tell from the format of these equations, it's not the vector equation, it's not the parametric equation, these are symmetric equations. And then in them being symmetric equations, we can quickly tell something because this x stands alone in the symmetric equations. We know that our a is 0. So let's rewrite these in the format that we're accustomed to. So we need to have y minus something over something. So this is y minus -1 over 1 equals, and this needs to be z minus something, that's z minus 0 over something, which is 1. Now from that, we can pull out some more information. We could figure out what the vector L is that's parallel to the line, as well as we could figure out a point that is on the line from this information that we have here. Now we could have done that in this form up here, but I think it's just a good practice for you to put your symmetric equations in this form where you can clearly see what everything is. So now we want to find the distance between this point and this line. So let's write down our formula again. So D equals the magnitude of L cross P naught to P1 all over the magnitude of L. So we have a few things we need to find. We need to find what our L is. We need to find this vector, find that cross product, and then find some magnitudes. So our L we can see is, remember, this tells us that A is 0. And then we can see what B is, that B is 1. And we can see that C is 1. So there's our L. We have our P1 already. Let's find what our P naught is. So P naught, we can use any point we want to on this line, and the line has infinitely many points on it, but the easiest thing is to use the one that's explicitly what we see right here. We see that x is -2, or x naught, excuse me, is -2, and then y naught would be -1, and then z naught would be 0. So that will be a good point to use, is that point right there. And now we need to find this vector P naught to P1, and we need the magnitude of L as well. So let's go ahead and find the vector P naught to P1. Now this is, if you found the wrong vector here it wouldn't, if you found P1 to P naught instead of P naught to P1, it wouldn't be a big deal, because when you take the cross product, you're still going to get a vector that is, you're going to get the wrong vector here, which will give you the wrong vector here, but it doesn't matter because you're finding the magnitude of that, and the magnitude is still going to be the same. So it wouldn't be a big deal in this scenario if you did it incorrectly, but we're going to make sure we do it correctly. All right, so P naught to P1. So we're going to do 2 minus the negative 2, which gives us 4, and then 1 minus the negative 1, which gives us 2, and then 0 minus 0, which gives us 0. And then let's go ahead and find the magnitude of L now, which is going to be the square root of 0 squared plus 1 squared plus 1 squared. So that's just going to be the square root of 0 plus 1 plus 1, or the square root of 2. All right, now we need to find a cross product between L and P naught to P1. So another thing here, if you found the cross product between P naught to P1 and L instead, it wouldn't be a big deal because it just points in the wrong direction, but its length is going to be the same as this vector right here. All right, so L cross P naught to P1 equals I, J, K, and L is, and a lot of you all will quickly learn how to do cross products faster than you see me do them. I'm just going to work, for the sake of everybody, I'm just going to work them all the way out for the most part every single time we need to do one, at least for now. When we get later in the course, then I will go through it a little more quickly and let you all work on it on your own. All right, so are those the correct vectors? Yes, and yes. Okay, so this equals, now we're going to ignore this I column and that I row, and we're going to do 1 times 0 minus 2 times 1. So 1 times 0 minus 2 times 1. Multiply that by I, then it's a minus sign. We're going to ignore the J column and the J row. 0 times 0 minus 4 times 1. Put our J, and then it's a plus sign. We're going to ignore the K column and the K row. 0 times 2 minus 4 times 1 times K. And here we have 0 and minus 2, so we get negative 2I. And then we have negative 4, but then multiplied by the negative gives us 4J. And then we have negative 4 right here, so minus 4K. So now we need the magnitude of this vector. So the magnitude of L cross P naught to P1 is equal to the square root of negative 2 squared, which gives us 4, and then plus 4 squared, which gives us 16, and plus negative 4 squared, which gives us another 16. So we get the square root of 36, which is 6. And now our D is 6 over the square root of 2. So the distance between that point that we were given, you can't see it anymore, but it was, oops, sorry, you can't see that either. The point was 2, 1, 0, and the line with the equations, the symmetric equations, x equals negative 2, y plus 1 equals z, is 6 over root 2. All right, so that concludes our 11.5, and we'll start 11.6 in the next video.